Hello everybody, welcome to the next set of videos on fluid mechanics. My name is Professor Brent Nanigay and I'll be covering the next section of the fluid mechanics reviews where we're going to shift our focus to microscopic fluid mechanics, which is different from what was covered in the previous sections on macroscopic fluid mechanics, which was more interested in sort of the bulk properties of the fluids. We're going to switch and transition to describing the fluid flow profiles within the fluid itself. Which we call microscopic fluid mechanics. So before we get into actually solving problems, we have to cover what's described in chapter 5 of the book we use for the sophomore level class, covering some of the differential equations that are going to be used. So this part, the microscopic fluid mechanics, is a bit more math heavy than the previous sections. And so we're going to go over the review of some of these different mathematical equations. Now, if you did the introduction material on the math previously in the previous videos, this will hopefully be an even easier review than it normally is. But the idea is we're going to talk about these different vector analysis and differential equations and how we're going to apply these to mass balances, momentum balances. And when we do this, this will help us derive what are called the Navier-Stokes equations, which is based on the sort of the momentum balances on finite elements of fluid, which is then we're going to use the Navier-Stokes equations to actually solve some problems. That's what we're going to be covering today in this video. So the first thing we want to go over is how we do differentiation with vectors. And the main one we're going to talk about is a del operator. So basically the del operator is just going to do the partial derivatives of, in this case, x, y, and z. When you put it together with a scalar, for example, as del s, you're going to now have the partial derivative of s with respect to x in the x direction, partial derivative of s with respect to y in the y direction, and the partial derivative of s with respect to z in the z direction. Now, in addition to this, we're going to also talk about things like gradients. And gradients are used a lot in different transport equations. You can imagine scalars such as temperature, which would be important in heat and mass, concentration, again, important in mass transfer, and it's going to be defined as a vector where the concentration or the temperature or the scalar is going to increase most rapidly with distance. And then the magnitude of that scalar is going to be equal to the rate of increase. So another way of writing this is if we have the rate of change of the scalar s with respect to the direction r is going to be the same as a del operator s dot sort of vector direction in r. Another term we're going to use is fluxes. So the flux is just mass, momentum, energy, anything are going to be that are considered in transport. Obviously, in this class, we're going to mostly be focused on momentum and mass fluxes. But the flux is just a vector that's going to be passing through, a per unit area. So the one we most likely are going to come across in this class would be sort of what we call this volume flux, or the flow rate across an area, which would just be equal to the velocity through that area. Now, if we take the magnitude of the flux across the entire surface area, which has and that surface area is going to have a normal vector, which is going to be n. We're going to have this sort of vector dot n, which is the normal vector, and then the surface area here. And then we said v is sort of this flux vector. So this is how we're going to calculate fluxes. Now the net flux, so the entire flux in and out of a system, it's going to be equal to how much the flux is changing with respect to each coordinate. And the way to describe that mathematically is going to be called the divergence of the flux. So divergence is written here. So the divergence of that flux vector here is just going to be the partial derivatives of that. So v, in this case, v, we're going to have vx dx, vy dy, vz dz. And another way of writing that is just the del operator dot the vector here. Now, if we're talking about fluid mechanics, which we're going to get to when we get to the equations later on in this video, if you take the divergence or the net flux in and out of a system, it's going to be equal to 0 for incompressible fluids. Basically, what comes in has to come out in terms of the velocity. Otherwise, you'd be accumulating material inside the unit volume or losing material inside the unit volume. So this is an important definition here. Now, if the flow is not rotating, so what that's going to mean is what's known as the curl or the del operator across the velocity is going to be equal to 0. So this is important. So if we're talking about irrotational flow and incompressible flow, we're going to have both the cross product of the del operator and the dot product are going to be equal to 0 if it's irrotational and incompressible. And this is going to represent pretty much all of the examples we're going to talk about in this section here is going to be irrotational, incompressible. And we're going to be able to use these definitions as assumptions and ways to simplify our equations later on in the video. Now, when we have the velocity is determined by some sort of gradient of a scalar, in this case, we have the equation here phi, which is called the velocity potential. We would just have the del operator times, the del operator of that, that gradient here, which would give us the velocity profile. So if you're able to do right here, del dot del phi, you just end up with this del squared here, which is also called the Laplacian operator, and that's really important. We're going to see this a lot today. So hopefully this is not completely new information, just again a very quick review on some of the math. You can refer back to these equations later when we're showing the full Navier-Stokes equations to kind of match up what we're talking about in the later slides with some of this math. That's basically all the math review we're going to do. We're going to sort of jump right into now applying these to fluid flow. So the last and one of the more important definitions we're going to have here is called the convective derivative. And this is really important because what it is going to be the derivative of the rate of change of some parameter, so some x, with respect to time following the path taken by the fluid. So if you imagine you're going to have this unit of fluid that we're going to be analyzing, and it's going to be the rate of change of that unit of fluid as that unit of fluid is moving in the flow. So one example we give here is density. It's very important. So if you've got the rate of change of density is going to be equal to the rate of change of density with respect to time, dt, the rate of change of density with respect to position x, dx, the rate of change of density with respect to y, dy, rate of change of density, z. So you've got sort of x, y, and z and time right here. So in this case, dx is equal to velocity in the x direction dt. So you can see how by using this dx here, we're sort of, the unit of x here is a function of as the fluid is moving with respect to time with some velocity x. And so we're sort of following the fluid as it goes in the x direction. Now, of course, by extension, dx here, if we did dy, that would be vy dt, for example. And so you can talk about the convective derivative in this case of density, dt, is just going to be dp dt, vx, dp dx, and so on. Another way to write that here is just the velocity, or sorry, the density with respect to time plus v dot, the del operator, and then density here. So this is an important equation here to talk about how density is changing as this little, infinitesimally small volume of fluid is moving in the flow. So we're going to now apply these concepts to, the first is to the mass balance, and then we'll move on to the momentum balance. So first, if we're going to talk about mass, so consider the an infinitesimally small volume, which is dV. So it's going to be dx, dy, dz, and where density is going to be constant, so constant density in this volume. So at dV, the total mass here is going to be density times this differentially small volume. Right, so density times volume equals mass. That's where this comes from. Now, the fluid flows are going to be bringing mass in and out of this volume, and the net flow out is the divergence. As we talk about, the divergence is that the sort of the net flux through a volume. So we can write that that statement here is this equation right here. Oh, excuse me. And so because dV is a constant volume, right here, we can sort of simplify it and write it like so. Or we can expand using what the definition of this sort of del operator is. We can expand to this equation here. So this is going to be basically our differential mass balance right here. You can see it's basically the change of density with respect to time, and then how the mass is flowing in and out in the x, y, and z directions. And all of that has to equal 0 because we're going to say what mass balance, and what comes in has to come out. Okay, so if we look at this term, for example, the x right here, this term can be divided into two different parts where we break up the density and the velocity in the x direction here. So we actually have density times the partial derivative of Vx with respect to x plus Vx times the partial derivative of density with respect to x. That's how we can break this term up. And we can do that with each of these forms here. Because we're going to be talking about constant density, right, this term will go away. We'll lose this sort of the variations in density with respect to position. And we're going to only be left with now the velocities. So this differential mass balance sort of becomes the divergence definition, where we're just basically having our rate of change of velocities with respect to the different directions. And that also has to equal 0, again, because the mass balance has to equal. In our definition of divergence, we said it has to equal 0 for an incompressible flow. Okay, so now we're going to move to the differential momentum balance, which is a little bit more work to get through. So the differential momentum balance, we're going to start off by basically doing a sum of forces. So we're going to consider that same sort of fluid element. We're going to use Cartesian coordinates here, but you'll know there's also these same analyses done for both cylindrical and spherical coordinates. We'll see an example later of what this looks like in cylindrical coordinates, but we're not going to go through the derivation in cylindrical coordinates. So we'll work here with just Cartesian coordinates. So because sort of this fluid element is moving with the fluid, we're not going to need to worry about convective transport. We're just basically going to be looking at the sum of forces here, which is going to be, in this case, just in the x direction. We're going to start off in the x direction, and you can see by extension how we look in the y and the z directions. But in the x direction, we're going to have the sum of all the pressure forces, plus all the normal stresses, plus the shear stresses, and plus any sort of body, which you can think of like gravity, for example. And all of this would have to equal 0. Okay, so we focus on each term separately. So we're going to walk through this. So first, we're going to start off with pressure, this term here. Now, just for simplicity's sake, it's three-dimensional. When we get to the end, we'll have a three-dimensional Navier-Stokes equation, but we're going to focus on just x and y just for simplicity. So we're going to take it into a two-dimensional analysis here. So if we look at pressure, we're basically going to have the pressure right here at xy along this sort of along y minus the pressure at x plus delta x. So just down, if we're thinking the x direction, pressure on one side, and then the pressure on the other face that's just delta x away from this one right here. And then if you look at how this is written, you can break this apart, you can cancel terms out, and you eventually end up with the pressure term is going to be the rate of, the derivative of pressure with respect to x, delta y. Now again, if this were three-dimensional, we'd have delta x, delta y, delta z. But again, for simplicity, we're just going to have two dimensions, delta x and delta y. So this is our term for pressure right here, how pressure changes with respect to x. Now, if we're going to look at the different stresses, we have this, you can imagine here, this is our control volume. So again, x is going this direction, and this is our delta y right here. So delta y, delta x. And we're going to have sort of velocities moving through. We're going to have two different ways of writing this. You can think of u would be the velocity. We'll also write u sub x, denoting the velocity in the x direction. And then sometimes we'll write v, which would be the velocity in the v direction, or we'll write u sub y for the y direction of velocity. But we have all these velocities coming in and coming out. We have all the pressure terms pushing on each side. We've got all the shear stresses and normal stresses on this volume here. So if we look here at the body force now, so we already have our pressure term, we put that here. If we look at the body force here, it's going to be the density of gravity in the x direction. And again, normally it would be times the whole volume, but again, we're doing two dimensions, so we're going to turn that volume into just delta x, delta y. So density times gravity times delta x, delta y is going to be our body force. All right, let's look at the normal stresses. So again, we look at this term here. We're going to have the normal stresses. That's the stresses pushing on either side here. And the way we write this, if you remember from the earlier videos, is it's going to be tau xx. So we're going to have tau xx at x comma y, and then it's going to be delta y across that whole face, the whole delta y face here. And then we're going to have plus the tau xx at x plus delta x, so just on the other side of this differentially small rectangle here. If we combine all this, we get the partial derivative of tau xx with respect to x, so how this sort of normal stress is changing as a function of x, times again delta x, delta y. If we look at the shear stress, again, very similar, except now instead of the delta x, we're looking at this delta y term here. So x right here, x, y plus delta y minus x comma y, and delta x in this case instead of delta y. But in the end, you get a very similar term. You get the partial derivative of tau yx with respect to y and then multiplied by delta x, delta y. So very similar, but now we're talking about shear stresses, which again are going this way as opposed to normal, which is pushing on directly on the normal surface in the x direction. Okay, so if we combine all of that, our pressure terms, our different stresses, and then our body force, we get this term here. Again, all in 2 dimensions. If we group terms, we'll end up with this equation right here, which is just how our pressure, our shear stresses, our normal stresses, our body force, and then all times the area of this rectangle. Again, in 3 dimensions, it would be the volume, the control volume would be here. Okay, so now we're going to plug in the definition of this convective derivative to look at how the net change of momentum is coming in and out of the system. Remember, this is a momentum balance here. So the change in force here is going to be equal to our density, the area that we're talking about, and then the convective derivative of velocity with respect to time. So if we expand our definition here, which we had before, this is the sum of our forces that we got from the last slide, because we were able to divide both sides by delta x, delta y. We end up with this equation here, the convective derivative times density equals what we had just put together from the last slide with pressure, body force, and then the shear and normal stresses. Okay, so now we're going to bring in viscosity. So if you remember from the earlier lectures on fluid properties, this viscosity is related to the stresses here by mu, which is the viscosity here. So the stress here is equal to the viscosity, mu, and then the partial derivative of velocity with respect to y. Partial derivative of x, the velocity in the x direction with respect to y. So if you're going to look at tau yx, for example, this is how it would break up. You'd have the viscosity times the derivative of the velocity in the x direction with respect to y plus the velocity in the y direction with respect to x. Now, if you're looking at tau xx here, it would be, both of them would be the derivatives of ux with respect to x, or just 2 times the viscosity derivative of velocity with respect to x. Okay, so if we take this, we plug that back into the equation we had before, which was this equation here, we will end up with now everything in terms of viscosity and velocity. So again, we just changed nomenclature here. Instead of u sub x, we're just going to call that u, and instead of u sub y, we're just going to call it v. So again, u is going to be the velocity in the x direction, v is going to be the velocity in the y direction. And so now we have this equation right here. Pressure, our stresses, our body force right here, and then the convective derivative is right here. Okay, so we're going to rearrange this a little bit, and you'll see why in the beginning it might not make much sense while we're breaking things up the way we are, but trust me, it's going to go somewhere that allows us to simplify this equation a little bit. If we take this term here and we break this apart, so it's 2 times this term, so we're going to put them each individually, one over here, and then we're going to also break this term up here, right here, and right here. So we're just expanding this equation. And then we can start to group things together. So once we group things together, we can sort of see we're going to move this term here over here. We're going to move this one over here. We're just sort of rearranging. And we're going to take this equation here. Instead of saying partial with respect to y times the y velocity with respect to x, we're going to swap these. And we're going to say now it's partial with respect to x. And we're going to have velocity in the y direction with respect to y. We're just sort of swapping these two right here. So again, just swapping, we're grouping things. And the reason we group things like this is because now if we look at this equation here, these are both partial with respect to x. So now we can take partial with respect to x of du dx plus dv dy. If you remember our continuity equation, this has to equal 0 from our continuity equation. So that allows us to cross out this entire term here. we still have our gravity term hanging out here. So that's why we kind of split things up and moved them the way we did, so we could cross out using continuity right here. So that gives us this much more simplified equation here, where now we have these sort of second derivatives. We still have our pressure, all of our stresses are here, and our body force here. Now on this side of the equation, the convective derivative, we're going to expand this based on the definition of the convective derivative. Again, now only in 2 dimensions instead of the 3 dimensions we originally talked about. But if we break this up, we have the x direction velocity with respect to dt, ux, and then the derivative of ux with respect to x, the y direction velocity, ux with respect to y. This is the convective derivative here. So now we have both sides of the equation for the momentum balance now. If you were to expand this into 3 dimensions, if you compare this here, this is again, it's 2 dimensions, but you can imagine we could add here a z direction, uz, dux, dz. That would end up here. So we can expand this a 3rd dimension by just adding the z's here. And then here's the dux, dz. This top one here is all relating to the x direction, ux, 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 ux. See all the velocity in x direction. If we were to do the same thing but in the y direction, you'd see we'd get this term right here. These are all y's, and then here's the z direction. So these 3 are the Navier-Stokes equations in Cartesian coordinates. So this is your starting off point for our sort of microscopic analysis in this chapter here. Now, I've mentioned before, there's other forms for cylindrical and spherical coordinates. We're not going to go over those derivations, but just know they look slightly different. So in cylindrical, you'd have, for example, uz, ur, and u theta, and they would look slightly different because of the different derivations in the different coordinate systems. Okay. So again, in the book we use for the sophomore level class, they just as a reminder, they use sigma here instead of tau for the stresses. And this is how they write it. Now this last term here, for incompressible fluids, which I mentioned we're going to be dealing with incompressible fluids, this term goes to 0. So the whole Navier-Stokes equations are more represented by this, and because this term goes to 0. Also when performing the analysis on the shear stresses in 3 dimensions, there's a total of 6 shear stress components and 3 normal stresses. And we call this sort of 3 by 3 matrix a tensor. Now of the 6 shear stresses, only 3 are actually independent, because if you look at tau yx, that's the same as tau xy. And so keep that in mind if you're going back over the analysis and how you derive this for sort of 3 dimensions. Okay, so now we're going to apply these Navier-Stokes equations to actually solve for the fluid flow profiles in what we call viscous flow problems. And viscous flow problems, we're basically talking about how viscosity is really what's dominating the flow profile here. So we're going to actually derive this shape of this curve here. We're going to talk about and it mostly involves laminar flow. In the next video, we're going to discuss turbulent flow, which is a little bit more complicated. But with laminar flow, we're going to be able to use the momentum balance and the continuity equations. We're going to talk about how do we make assumptions to simplify those equations. Now, those equations admittedly are very, very long and very, very scary looking. But by the time we use all of our different assumptions, most of that stuff crosses out, and we end up with relatively simple equations to then just do basic calculus on and solve. So we're going to work on a couple examples of how we do this. So in the book that we use for the sophomore level class, this is called Chapter 6. Again, we kind of covered this already, how to derive the equations of motion from the conservation of mass and momentum. Now what we're going to do is we're going to show these equations again, and as you can imagine, these equations can be very, very difficult to solve analytically, meaning there's a lot of stuff going on there. But through the assumptions that we're going to make and through some very defined problem sets, you're going to see that a lot of that can cross out, and we're going to be able to then actually solve them analytically. Okay, again, we're going to mostly talk about viscous flow, which also means laminar flow problems. So again, the viscosity is dominating the flow, and it's going to flow in nice, slow, laminar flow. Now, as chemical engineers, we're mostly interested in turbulent flow and actually many of the applications, but it's very important to understand how laminar flow problems are solved just because it has a lot of applications to other classes. So just keep that in mind. In fluid mechanics, in chemical engineering, often we're dealing with turbulent flow, but these laminar flow problems are still very important to understand how we go about solving these equations. Okay, and there's two types of flow. We're not really going to talk about this because this will show up in the examples, but there's fluid flow where you've got basically an applied pressure causes the fluid motion. So you can imagine a pipe, and you have a pressure drop, which is pushing the fluid through the pipe, or you have a different type of flow where a moving surface drags adjacent fluids. You've got, say, a plate sitting on a fluid, and you're dragging the plate across the surface of the fluid, and that's what's causing the fluid to flow. Okay, so the equations we're going to use, these are the same equations we just derived in a couple slides later. We've got our differential mass balance, where the divergence, the velocity is going to be equal to 0. And then there are three Navier-Stokes equations in x, y, and z. Again, they're going to look slightly different if we're using cylindrical coordinates. As you could expect, if we're going to deal with the pipes, we're going to be using cylindrical coordinates. And we'll have an example of that a little bit later. Okay, so how do we go about solving problems? Well, the first one is going to make reasonable simplifying assumptions. So, for example, when the problem statement lays out the problem, we're going to try to set up the problem in such a way that allows us to, for example, put gravity in only one coordinate. So, okay, if we arrange our system so gravity is only acting in the z direction, for example, that will allow us to cross out, or in the y direction or the x direction, however we want it, it's going to allow us to cross out all of the gravity terms except in that one coordinate. Maybe a better simplifying assumption than the gravity one is going to be try, if possible, to align the flow so it's only in one direction. So for example, if you've got a pipe on an incline, you might want to adjust your coordinate system so that your x direction is maybe at an angle. So rather than having the fluid flowing both x and y, you can tilt your coordinate system by whatever angle the pipe is tilted at, and then you're going to only have fluid flow along the pipe axis, which allows you to basically ignore all the other velocity terms, which can simplify your equations. Once you figure out your coordinate system, your simplifying assumptions, you're going to write the equations of motion, both continuity and momentum. You're going to be able to use those assumptions to simplify those equations, and then you're going to integrate the equations to sort of solve for the dependent variables, pressure, velocity mostly. Once these expressions are going to contain arbitrary constants because we're going to be integrating. And remember, when you integrate, you're going to have some constant terms fall out. So if you remember the Navier-Stokes equations, there was second derivatives in there. So that means we're going to integrate twice. We're going to get two constants for velocity. Because we have these constants, we're going to have to also define boundary conditions, which are going to allow us to solve for those constants. And you'll see there's various types of boundary conditions that we can use. And that's really the key part of these problems. If you identify the wrong boundary conditions, it's going to take you down the wrong path of solving the problem. Once you solve for the constants, you basically then rearrange your equations and solve for the desired parameter, pressure, velocity. Okay, so probably the best way to learn this is to take a look at an example here. So what we're going to do here is we're going to have flow between parallel plates. And the picture down there sort of shows what we're dealing with. We've got a plate on the top and a plate on the bottom, and we're going to have, we have y going up, x going this way, z would be coming in and out of the screen. And the flow is, because of a pressure gradient, is going to be pushing the flow this way, from left to right. So the plates are rectangular. We're going to assume that they're very large in the z direction, so we're not going to worry about effects because of the edge of the z. And so one example for this is if you have polymer being extruded into two very thin plates. So the plates are large in the z direction, but maybe the space between the two is very thin. Now, what we want to do is determine the relationship between the flow rate and the pressure drop between the inlet and exit. So here's the pressure drop. There's going to be higher pressure here, low pressure here, and that's what's pushing the fluid this way. So we're going to determine the relationship between the flow rate and the pressure drop here, and then determine the velocity flow profile. If you remember before, we've got sort of no slip conditions at the plates. And so since the plates aren't moving, the velocity will be 0 here and reach its maximum somewhere in the middle and go back to 0 down here. So we want to actually derive the mathematical expression that would allow us to figure out what is the velocity at any point in y. Okay, so So let's make some assumptions on this. So we're first going to look at that cross section of the fluid. So we're going to call the depth, so it's going to be a depth of 2D. So if you imagine, we're going to take the center line between the two plates, we're going to call that 0, and then we're going to have 1D going up and minus D going down. So total, we're going to have 2D depth, and then the length is going to be some length L. So our first assumption, steady state Newtonian fluid with constant density and viscosity. So this is very, very important. We're going to mostly use this in the examples we do here. You can imagine why this is so important. If density is not constant, there's a lot of things that can't be assumed in the next examples, in the next equations. Same thing with viscosity. So hopefully you appreciate how important this first assumption is. The second assumption, entrance effects can be neglected. So basically, at the point that we're analyzing the fluid flow, the fluid is fully developed. So there's no entrance effects, there's no exit effects. We're just looking at the fully developed flow sort of in the middle section of this, of these two plates. Because of that, we're going to say fluid is only flowing in the x direction. So there's only velocity in the x direction. So Vy and Vz are both 0. Step 3, or assumption 3, is that all locations z directions are similar to the slice we're analyzing. So basically, as we come in and out of the screen, every slice is going to be the same. So what that allows us to say is that the change of velocity in the x direction is independent of how far in and out of the board we are, or the derivative of Vx with respect to z is going to be 0. 4, gravity acts only in the y direction. So that means gravity, the y component of gravity is equal to negative g, and the x component and z component of gravity are both equal to 0. And assumption 5, due to the no-slip boundary condition, Vx equals 0 at y equals plus or minus d. So y equals plus d at the top, y equals minus d at the bottom. The velocity is going to be equal to 0 at both of those points. All right, so let's start off with our mass balance equation, see how we can use this. So remember, our continuity equation is equal to this. If we use the constant density assumption, which we did when we derived this, basically constant density means density goes away, and all of these densities can get pulled out of the derivatives, divided over here by 0, so they basically all cancel out, and you end up with just the velocity terms equal to 0. Now in our assumptions, we said a velocity in the y direction, velocity in the z direction are both 0, so that means we can cross out both the y and the z, and we end up with our continuity equation just saying that the rate of change of velocity in the x direction with respect to x is equal to 0, which is basically saying that velocity in the x direction is only a function of y. So the velocity is going to be changing only as we go up and down the plate, not left and right, or not in and out of the board. All right, now let's look at the momentum balances. So again, these equations, they look very large, very unwieldy, but you'll see how we're able to use these assumptions and cross most of this stuff out. So the first thing, which was what we got from the continuity equation, which was the Vx dx is equal to 0. This is what we just talked about. If we use that assumption, we can cross out both of these terms. So those both go to 0. If we use our steady state, which is assumption 1, anything that has a time derivative goes to 0. If we say velocity y and velocity z are both 0, so only velocity in the x direction, we cross out most of the rest of the equations. Assumption 3, which was that the velocity is not changing in the z direction, lets us cross out this part over here. And our last one, which was the gravity is only in the y direction, so gx and gz are both equal to 0. That allows us to cross out these terms here. So you can see most everything crosses out in the z portion. A lot of it cancels out in the y portion, and a good amount of it crosses out in the x portion as well. And so now we're going to separate these out and take a look at each of these individually. Okay, so there's our x component. All this eventually simplifies into, then the left side is all 0, equals our pressure drop plus viscosity second derivative of Vx with respect to y. If we rearrange this, we get pressure drop equals this. So this is going to be our equation that we're going to use to try to solve for Vx, is right here. You see, this is much more manageable than the entire equation that we had to begin with. If we look at the y component of the Navier-Stokes equation, that basically says that our pressure drop in the y direction is equal to, or not our pressure drop, sorry, our change in pressure with respect to y is equal to the gravity term that we have here, the body force. So we end up saying that density times gravity is equal to our change in pressure in the y direction. And last, if we take our z, we basically say the only thing that's left over is that the pressure term in z is equal to 0. So really nothing's happening in z, in the z direction. So we don't even need to worry about this part of the equation. Okay, so let's look at our velocity distribution. This is what we're trying to solve. We're trying to get our velocity profile here, which is the top part. Then if we want to look at pressure, we've got here our y direction, and then nothing's happening in the z direction. So again, let's take a look here. Okay, so here's our equation in the x direction. How do we solve this? And this is just basically, hopefully, some review on calculus. We're going to have this equation. We're going to need two boundary conditions. So I wrote 3 up here, but these top 2 are kind of this bit of the same, which is just, this is our no slip condition. We're saying when y equals d or y equals negative d, we're going to have velocity in the x direction is going to be 0. That's the no slip condition. Now, because the top and the bottom are both equal to 0, and the maximum, you can imagine, is going to be right down the middle, this is the flow profile is going to be symmetric. Now, what that means is if we look at how the rate of change with x with respect to y, it's going to look sort of like this, like a parabola, which means right there, right down the center line where the max velocity is, the derivative of velocity with respect to y is going to be 0. So this is basically saying we have a maximum or minimum right down the middle of the flow. So that's what this boundary condition is saying. And you'll see why this boundary condition is so helpful as we go through the example here. Okay, this step we're just rearranging. We're moving the viscosity over to the left-hand side. Okay, and then we're going to integrate. We're going to take the derivative with respect to y of both sides. Now we don't need to deal with this because this is sort of you can think of it as a constant, so we don't need to integrate this. So when we integrate the left-hand side, we just get a y plus c1. And on this side, we cancel out one of the derivatives. Now we just have dvx dy. Now we have this c here. We can either handle the boundary condition now if we're able to, or we carry the c down further and then solve for 2 different constants. And we'll see an example of that next. But because we have one of these boundary conditions here, right, which says we have a boundary condition that uses the derivative of velocity, we can directly solve for c1 right now. So we plug in this boundary condition here. So if we plug in 0 for y, that goes right here, and we say the derivative is 0, that goes here, we can now solve for c1, which just basically says c1 equals 0. Okay, that's easy. That means we can cross out c1. We no longer need to worry about this. And we can do the second round of integration to get velocity by itself. If we do that, now we get 1/2 here, y squared, plus c2 equals vx. Now we need to solve for c2. We use the other boundary condition. I'm going to use the positive d here. So if we use the positive d, we plug it in here, so we get d squared, that comes from the y squared, plus c2 equals 0. So if we solve for c2, we end up getting this right here. Now we can take this c2, plug it right back in, and now this is our equation for velocity in the x direction. If we just rearrange some things, we can group the y and the d here. And then because pressure drop, remember, is usually given as negative dp dx, we're going to just flip the sign here, and we're going to get this final equation here, which is our velocity profile as a function of the pressure drop and the distance between the 2 plates. So you can see here, this looks like a parabola, and this looks parabolic. So this is how you would solve the velocity profile in this case. Okay, so for the next example, let's look at a slightly more complex one, and we're going to work on cylindrical coordinates just so you see what cylindrical coordinates look like. So this is example 6.7 in the textbook that we use for the undergraduate class, and it's going to be analyzing this sort of this extruder that's used in polymer processing. So polymers are very viscous, so usually all the flow through it is going to be this laminar, and it's going to take high pressure to push them through this die. And so this is what the extruder looks like. You're going to be pushing the polymer sort of through this outer pipe here, and then inside you're going to have a dye right here that's where the polymer is going to be coming through. Right. So what is this? So basically you can imagine we're going to be doing a flow profile of a pipe, but then has sort of a core, another pipe. So it's just going to be the flow around the outside shell of the pipe that's between the center part and then the outside here. So clearly this is going to be easier to solve in cylindrical coordinates because it's basically a pipe. Now the Navier-Stokes equations look like this in cylindrical coordinates. You'll notice they look a little bit different, and this is just a result of doing the derivation in cylindrical coordinates rather than Cartesian coordinates. But it's very similar. If you look at the R component, you see they're all VRs here, and you get an extra 1 over R every now and then. You get an extra, so there's some extra terms in here that you just got to pay attention. Don't worry about the derivation here though, just use these equations and go with it. But just be aware there are other additional terms. You can't just use the Cartesian coordinates Navier-Stokes and switch all the parameters from x, y, z to r, theta, and z. You have to use these actual equations. And then this is the mass balance. Notice there's an extra, these 1 over r's here. Okay. So this is what we're going to simplify that dye into this diagram here. So this is how you'd form a tube polymer. You're going to have this, the polymer is going to be pushed through. There's going to be an outer pipe here. And then in the middle, you're going to have this fixed inner cylinder. So the fluid's going to be flowing around in sort of this ring shape around the outside. And there's going to be a velocity profile sort of like this. You're going to have no slip here at the top, and then no slip here at the center of this ring here, the inner cylinder. So the inner cylinder is going to have a radius of 1, and the outer wall is going to have a radius of 2. And so you're going to be flowing between R2 and R1. If you didn't have this inner dye here, a regular pipe, you'd imagine the velocity profile is going to look a lot like the plate profile we had before. It's going to be just like a parabola with maximum right down the middle. But in this case, we don't have the maximum down the middle because we have the dye there. So how do we handle this? It's going to be very, very similar to what we did before. We're going to first make assumptions. We're going to take our Navier-Stokes equations. We're going to see how those get canceled out based off our assumptions, and then we're going to use calculus and boundary conditions to solve for the velocity profile, in this case in the annular space here. Okay, so what assumptions are we going to use? Well, in this case, if we look at our coordinate system, I'll go back to the slide before. If we look at our coordinate system, we have R is going here, Z is going down the direction of the pipe, and then theta would be sort of the angle around the annulus here. So in this case, our velocity is only going to be in the z direction. So velocity in the radial direction and velocity in the theta direction would be 0. Hopefully you understand how that makes sense, right? The velocity in the r direction would mean you'd have fluid flow pushing outwards, which doesn't make sense in this case because it's flowing down the barrel of the pipe. And theta would mean you'd have sort of this rotation around the pipe, which we're saying is not rotating, it's just flowing right down the pipe. So VR and V theta are both 0. Gravity acts downward. So there is no gravity in the z direction. Now there is gravity in terms of theta and in terms of r, but we're going to ignore that for now. And then we're going to have velocity in the z direction is independent of angular location. So the velocity in the z direction with respect to theta is equal to 0. Again, there's no velocity gradient around the annulus. If you go around in the angle, every position, as long as it's at the same radius, is going to be the same no matter what the angle is around the pipe. So velocity is not going to change around the pipe. These are the assumptions. You can see they're very similar to the assumptions we had in the last example. So let's take a look at our continuity equation, right? Constant density, that's going to go away here. We're going to say, we said velocity in the radial direction is 0, velocity in the theta direction is 0, and so we're just really left with velocity in the z dz, which allows us to simplify to this, dvz dz equals 0. Very similar to our last example. Momentum balance. We're going to take a look here at the radial momentum balance and the theta momentum balance. Now, if we were to go through the process and cross out everything that these assumptions allow us to cross out here, you'll notice that only the gravity terms and the pressure terms are going to not cancel out. And that should make sense, right? Everything here is VR. Everything with a VR and a V theta gets crossed out, which just leaves pressure and gravity here, and then pressure, theta, gravity here. Those don't cancel out. However, those two terms, the pressure sort of as a function of radius, and the pressure is a function of theta, and the gravity is a function of radius, and the gravity is a function of theta, don't really give us any information that's necessary in this problem. So we can sort of ignore these equations because they're not going to give us any useful information. Now, if you needed them in a problem, you can always go back and use these equations to solve what you need to solve. But in this case, we don't need them. However, we're looking for the velocity profile in z. So this is the momentum balance that we're going to work on. So if we take this and we look our assumptions, again, this is the time derivative goes away like normal. Everything, we said VR is 0, V theta is 0, and because of continuity, we know dVz dz is also 0. So everything over here cancels out. Oh, excuse me. Pressure stays here, pressure in the z direction. So this is our pressure drop. And then we're going to cross this term out here, right? Because we said velocity is not a function of theta. And we know velocity dVz dz also cancels out. So everything crosses out, and then there's no gravity in the z direction. So all these cancel out, and we're just left with this here, which is just dVz as a function of radius. So much more manageable than this entire equation. Okay, so how do we solve this? This is going to be a little bit more complicated, but not significantly more complicated. It's just calculus and algebra at this point. We have this equation that we're going to solve because we're going to try to get Vz, and we've got our boundary conditions, which are just when radius equals r1, that's that inner diameter, the inner radius of the die. The velocity is going to be 0. And then radius 2, which is the outside, velocity is going to be 0 there as well. I'll just go back here and show, right? Radius 1, 0, radius 2, 0 as well. Okay. So let's go back to our equation here. So we're going to rearrange this. We haven't done much here except sort of rearrange parameters, moved our density, or viscosity over here, moved radius over here, and then moved dr over. That's all we did here, rearrange this. And now we're going to do our first integration. That's going to give us 1/2 r squared. We do our first integration, plus c1, and then we're left with r dvz dr. Okay, notice how this turned from I forgot to mention this last example, this turned into a total derivative instead of partial derivative because we know that velocity is only a function of radius. So that allows us to switch over from the partial derivatives to this sort of derivative here. Now in the last example, we were able to solve for C1 directly here because we had a boundary condition that talked about this, the first derivative. In this case though, we don't have that same boundary condition. We don't actually know if the maximum of the velocity is going to be right in the center between those two, between the two cylinders. So we don't have a boundary condition that allows us to solve directly. So we have to keep C1 around. Okay, so we keep C1 around. We're going to divide by r to get that over here. So that knocks out this r squared to just r, and then we have C1 over r. If we do our next integration here, that'll give us now we have 1/4. And here we're going to swap the negatives on here because we're going to switch the pressure drop to negative like we said before. And now we have r squared. And now we have a natural log because we had 1/r here. So that's what makes things a little bit messy here. We have natural log plus C2 equals Vz. Okay, so now we have Vz, both of our boundary conditions here are Vz. So we can go ahead and solve the C1 and C2 by plugging in each of these different boundary conditions. So if we were to do that and solve for C1, you end up getting C1 looks like this, which looks kind of messy. C2 ends up looking like this. You can see C2 has C1 still inside of it. So to get C2, you'd plug this in here. So we're not going to go over this in detail because you can see how much algebra this is gonna get. But if you plug all these in and you simplify everything, you get this equation here, which is the velocity in the z direction is equal to 1/4 viscosity, the pressure drop in the z direction, and then the ratios of the natural logs of the radius with the inner radius and the outer radius gives you the velocity profile. If you were to plot this, just as an example here, this is what the flow profile would look like. It looks like two parabolas. We're right here down the center. This is where that inner cylinder is. And so if you notice at first it looks like a regular parabola, but actually if you look, the center line between the two cylinders would be here. And you see the flow profile is actually shifted. The maximum happens a little bit closer towards the inner radius and the outer radius. So it's a good thing we didn't make that assumption that the profile was symmetric, because it's not in this case. And that has to do with the geometry and the shape of the cylinders. So that finishes up our quick intro and summary of viscous flow problems in Navier-Stokes. In the next video, we're going to talk about similar analyses, but what happens when the flow is turbulent. You'll see it gets a bit more complicated. So thanks, everybody, and I'll see you in the next video.